Hi, it's Adam from Affinity Energy. We're doing a webinar today called Making Sense of Solar Data. How well does your plant actually function? We're going to talk a little bit about real-time SCADA and the data that's generally available from it, how to interpret it and use that data so that you can make some meaningful analysis on what's going on inside your plant and hopefully find the root causes that will help the plant run better. As a quick introduction to Affinity Energy, we are a control systems integrator, and our business is primarily focused around critical power applications, including data centers, hospitals, universities, and the group that I work in is focused on PV solar, monitoring, instrumentation, and controls. We've been in the business for about 16 years now, and have worked on sites from smaller than 1 megawatt all the way up to 550 megawatt sites, so we've cut quite a breadth of experience in both controls and instrumentation for solar. So I operate best in a world of analogies, and we think about in the morning you get up, get in your car, start the car, drive to work, and as long as the car starts, you think to yourself, everything must be okay. The car started, it runs, I got to the office, I got back home, everything's fine. But from a practical reality standpoint, just the fact that your car starts in the morning doesn't really say much about whether or not the car is running well. You can take data from your car's operation. If you're one of the kinds of people that saves your gas receipts, writes down your mileage on every receipt so that you can figure out what your miles per gallon is from one tank of gas to the next, that will give you some indication as to whether or not your car is running well. But the hidden aspects of it that you don't see when you're doing that calculation is how you were using your car from one tank of gas to the next. If you're all highway miles driving from Charlotte to Chicago and back, you're going to get different gas mileage than what you're going to get driving to the office in the morning and home. So because your gas mileage varies from month to month, gives you some indication of whether your car is running okay, but it doesn't tell you very much without the context of how the vehicle was being used. Early in my career, I was given a challenge when we were building a 290 megawatt solar site. We had the first electrical block, or the electrical feeder, running, and we had about 30 megawatts online. And the energy assessment over the course of the first month of running the site was that the site was coming up about 1.5% below where the pro forma was, where energy should have been. So as a result, I got a call from the manager of the engineering department asking me to look into what the root cause of the problem might be, if this was going to be a problem that was going to scale with the site. We only had 10% of the site online, and once we got to full capacity, this was a problem that would have cost the company a couple $1,000s a day in underperforming lost revenue. So could I look in and figure out why exactly that we were coming up short on energy? And the SCADA data that I had available to me was telling me that the inverters were running as they should have been, but the output from some of the inverters was less than what we expected it would be. So I couldn't see very much from SCADA about what was going on. I could see that our control system was commanding the inverters to full output, but the inverters weren't getting there. And that could be a DC health issue, it could be a combiner box offline, but of 24 PCS shelters, so 48 inverters, the output from each of them varied a little bit. So there was an inconsistency to the inconsistency. And finding the root cause within that, I could see that the control system was commanding them all to operate at the same output, but they weren't actually getting to the same output. So the next step was getting a tech, an on-site commissioning tech, to go out, put a meter on the output, the analog signal coming from the control system, to command the inverter, and we verified that it was where it was supposed to be, but the inverter still wasn't at full output. So we did a follow-on test with the process meter, where we drove a 4 to 20 milliamp analog signal into the inverter, and we found that from one inverter to the next, 19.1 milliamps might be required on inverter 1, whereas 19.05 might be required on the next one, and 19.2 might be required on the third one, just to get to full output. So it should have been 19 milliamps. All the documentation said it was 19 milliamps, but we found that in practice, the inverter behavior was different than what was expected. And we had to bias up the output for all the inverters at the site so that we could get them to full output. So that was an example of a really obscure, hard to find problem that would have turned into a very expensive problem if we couldn't find the root cause of it. But it was a very nuanced problem that was not at all obvious where the root cause might be. So it took about a week to figure out exactly what was going on. But we were able to solve the problem and get the plant to full output, and actually exceeded our pro forma energy calculations once the site was up and running. So it's a success story, but the simple fact is the data that was provided to us in our SCADA system, though rather comprehensive, still couldn't tell us exactly what the root of the problem was. So you need a little bit of understanding of the background for the data that you're getting in order to turn it into useful information. So solar plants are complex, and of the hundreds of inverters that we had at this site, if you have a site with trackers, there's thousands of moving parts. There are a lot of different places where something can be working less than 100%, and it's buried somewhere in the data, and you have to have some context to be able to figure out how to go out and find it. Common types of failures on a solar field, soiling, and soiling can take many forms. It might be consistent soiling over a good chunk of the site. This happens in North Carolina quite a bit in the spring. If a farmer's out next door turning a field, getting ready for planting, you get a whole lot of dust blowing across the site. You get relatively consistent soiling across all the modules, but at the same time, during the construction process, it's not uncommon to have a big blob of oil fall down on some solar cells while they're placing inverters or transformers, and that oil is not visible at the time. It's clear. It's hydraulic oil, so you don't really see it there, but it attracts dirt and it's super sticky, so that soiling in that area on one module will be persistent over time and get much worse. Cracked cells, sometimes those are easy to find, sometimes they're not very easy to find. The early failures after a solar site has been completed, the construction's been completed, the most common early failure that I've seen are loose or failed MC4 connectors where the crimp wasn't done properly, and we got a picture of what one might look like if it looks like it was all okay at the time of construction, but it wasn't a good electrical bond. You get a little bit of heat generation with current flowing through that, and the plastic heats up, separates, and you end up with a failed connector. So those are hard to find, but fairly common, especially early after the construction process. Those are the types of failures that you're going to see within the first couple months of the site running at full capacity. Shading is certainly an issue. Trees will affect shading on modules. Sometimes I've seen solar sites that are built underneath transmission lines, and the transmission towers will shade modules. So that's not uncommon, but finding those things can be a little bit tricky. And then lastly, blown fuses. Sort of in the same line of the loose MC4 connectors, blown fuses tend to happen early in the process if there is a wiring error. They don't generally happen on an ongoing basis unless there's an electrical problem, and certainly those things do happen from time to time after construction. So SCADA as real-time visibility into what's going on at the site. Years ago, SCADA was thought to be sort of the cure-all to keep the plant running well. It'll tell you what's going on in real time, but in fact, the SCADA system is only as good as the way the configurator interprets the data that comes into it. So SCADA is fantastic if it's very well thought out, very well implemented, but just giving you numbers as the numbers exist on the site without the proper context isn't going to give you a whole lot of value or ability to run the plant well. So among the last tests when construction of a solar site finishes up is the capacity test. And the capacity test verifies that the site is capable of making the rated power. So if you've got a 5 megawatt site, the capacity test shows that the site can run at 5 megawatts for a period of time. And that tells you that your inverters are reaching maximum output, but it doesn't necessarily tell you much about whether the site is delivering all the energy that it possibly could. So when I was first doing solar projects back in the very early days of solar, like 2009, we had very large sites with very rectangular arrays on very rectangular flat patches of dirt. And it was great because each inverter had 8 combiner boxes, and each combiner box had 12 inputs, and each of the 12 inputs was made up of 3 harnesses or 8 harnesses. So we knew we had exactly the same amount of DC coming into every combiner box and feeding into each inverter. So it was easy to see if one combiner box was underperforming because all of them should be giving you the same amount of current. But these days, those big rectangular easy sites, I see fewer and fewer of them. So now we have sites with discontinuous ground in terms of topo, so hills and valleys and things that you have to build around. You have different numbers of strings going into combiner boxes, and all of this makes determining the correct information from the SCADA system more difficult. As a result, your SCADA system will give you a lot of data, but it doesn't give you the information that you need in order to figure out whether things are running well. And the very small nuanced items can be very hard to find, especially when they're buried in trends of data over time that you can't see comparatively from one day to the next, or they aren't normalized in comparing data from one inverter to the next or from one day to the next. And these effects can be small. Like I said, 1.5% underperformance on the site I was talking about in the beginning doesn't sound like a whole lot of energy, but in that instance, it was a couple $1,000s a day worth of energy. So it was absolutely significant. And even today, if you've got an asset that's underperforming, you're giving away money that you could be collecting from the solar site. So the question of whether or not you can trust your SCADA system, the SCADA system is going to give you the data that it's collecting from the field, but the value of that data is very much dependent on the knowledge of the implementer to know how to interpret the data and give you meaningful information that will really give you some insight as to whether or not the site's running well. So for my early days in solar, the engineers who were doing the SCADA system and the control system spent quite a bit of time with the operators in the operations center just so we could verify we knew how they were using the system, where they would go to find the data, and help them be more efficient in finding underperformance. One of the things I encourage them and I encourage my engineers to do from time to time is to just pick a topic and do a deep dive on the data that's being collected to see if it makes sense, to see if the inverter current is changing over time, to see if the kilowatt hours from the inverter is changing on a day-to-day, week-to-week, month-to-month basis, and see if that aligns with what the overall site performance is. So the more time you spend dissecting the data and making some comparisons, the more knowledgeable you'll be in how the system works, and the more likely you are to trip across a problem that you can then go out and evaluate more broadly across a site or across your fleet of sites to see if that problem is persistent or if it's just an isolated incident. So don't ever hesitate to do a deep dive, parse through the data, see what you can find. It won't be obvious where the correlations or the causation is, but the more you spend evaluating what the data is, the more likely you are to find those problems. So there are 3 general areas that I would suggest are most impactful in figuring out whether a site is running well or not. The first one is finding opportunities to normalize the data. We have a graph here, I mentioned it earlier. This is looking at the currents coming from different combiner boxes into an inverter. You've got different levels for different combiner boxes, and it's really hard to know just by looking at this whether or not the data is correct or not. This really relies on the operator's knowledge of how it should be running, and that knowledge is fleeting. So normalizing the data, taking the current from each combiner box, dividing that current by the number of either watts or the number of strings that come into the combiner box will give you a way of saying, well, for each of these 8 combiner boxes, we should be getting 5.2 amps per string. Here's what the actual value is. So instead of looking at the raw values like we saw on the previous slide, here we're taking the total current divided by the number of strings from each of the 8 combiner boxes. And now you can see combiner box 1 and combiner box 4 are a little bit less than the combiner boxes around them, and that's indicative of a DC health issue. And you don't have to know how many strings go into it. It doesn't matter anymore. All you're doing here is looking for the differences to find underperformance, and you can get to that conclusion very quickly. So when we talk about data that can be normalized at a solar site, the easiest thing is combiner box current, like we just showed. And that tool can be most valuable when you are finishing up the construction process. So you actually want that early after construction is completed, because you'll find all the DC health issues before you go into performance test. And that way there you can be assured that you're not going to have any issues with your performance test. And that's the time that you're most likely to have a problem with DC health, is right after construction. So that's the best time to use that tool, but it can be used really any time to find the blown fuses and bad MC4 connectors we talked about earlier. Module bin class, if you end up with a site that has maybe half 310 watt modules, half 325 watt modules, just because that's what you could get, then normalizing for energy or for power from one area of the site to another is definitely doable. The last thing that's a little bit harder to normalize but can definitely be done is the DC watts behind the inverter, or the DC-AC ratio. So if I look at what the output of 3 different inverters would look like, I've got an orange curve that shows a 1-to-1 DC-AC ratio, a blue line that shows a 1.2, and a green line that shows a 1.4. And then I show above the flat surface what the irradiance would be for that different DC-AC ratio. You can see here that there is a period of time in which the inverter is at maximum output, and then there's a large window of time on either side of that where the inverter is ramping up or ramping down due to irradiance. And that ratio of how much time it's in clipping versus how much time it's in ramping is representative of the DC-AC ratio for that inverter. So you can do the math on a clear sky day to figure out what the effective DC-AC ratio is of any inverter, and that might be information that you can use to say things are running well or things aren't running well. That's probably the hardest normalization routine I've had to do at a site before, but I think it's also pretty valuable. Performance analysis and analytics, this is a challenging area because the easy temptation is to say, how is the site performing today compared to yesterday? You have trended data that might look the same over time, but the aggregation of the individual points within that trend are a more meaningful comparison. So to say that on March 1st of 2018, the inverter energy was this much, on March 1st of 2017, the inverter energy was this much, that might not be an accurate comparison if the temperature or the irradiance was different. So you might want to try to find a day within a week ahead of or behind a particular date to find similar ambient temperature and similar irradiance conditions in order to make a more valuable comparison. It's a little hard to find equivalent days, but again, the time of the year is important, but much more important is the ambient temperature and the amount of irradiance the site gets over the course of a day. So some of the critical insights, you might see over the course of a day that an inverter's output was good, and then it went to 0 for a period of time, and then it went back up. It may appear as if you've had a downtime event, but I would recommend that during that time you would want to also compare the output of the site from the site meter to see, in fact, if there was actually some downtime in an event, or if we just lost communications to the inverter. We didn't know what it was doing for a period of time. Communications was restored. The energy from the site is going to tell you the real story. What you get from the inverter might not be perfectly accurate. So identifying what components have underperformed is the real challenge, and using normalized data will help you do that. And then you can focus your O&M time and energy on improving the areas where you're going to have a lasting improvement in site performance. And then lastly, we talk about DC health. Over time, it's really easy to see if an inverter trips offline. It's obvious when you're looking at the output of the site that you've got a problem with an inverter. Even a combiner box is easy to determine. But the overall DC health of the site is more challenging to really understand. The DC-AC ratio that I talked about earlier is something that you could normalize the time spent in different conditions in order to determine an effective DC-AC ratio or a comparative DC-AC ratio. That's really going to give you some indication of whether there are DC health issues behind that inverter. You're still reaching the full site output. You're still making 5 megawatts for a period of time, but can that time window be increased? So can you get more shoulder energy? And then finding the individual problems on DC health is maybe one of the most challenging O&M tasks for a solar site. So there's been a lot of reporting recently with the really cool technology, putting an infrared camera on a drone, flying it over a site, and finding all of the module hotspots to help you go out and diagnose some DC health issues. I think it's interesting and indicative technology that'll give you some focus on where to look at a site. The thing I don't like about it is it doesn't give you a quantifiable value for whether the site is performing well or not. Really all it's doing is saying there are hotspots here or these modules are running warmer than others. And then you need to go do an investigation to see if you can visually see what's going on. But our approach at Affinity Energy has been to go out and do what we've been calling freelance data collection. Going out to a site with some DC CTs, clamping them on the individual strings and harnesses going into combiner boxes, and doing spot monitoring so that we have some real quantified values to say whether or not these strings are underperforming. This ties well with the normalization of combiner box data, where if we know there is a combiner box that has an underperformance issue, finding the specific string that is contributing or is having an issue can be expedited by just putting on some clamp-on CTs, looking at the data for a day or so, and then it's usually pretty easy to find the area, the specific string or the specific area of, or the specific harness that is having underperformance compared to the rest, and then you're only looking at a couple dozen modules instead of potentially hundreds of modules. Yeah, so in summary, I think we've got some solutions where there's a nice combination of taking real-time data, putting some wrappers around it to normalize it and understand better what it's really telling you, make it easy to find the differences from one area of the site to another. And then once an area has been identified where there's a potential problem, going out and doing the due diligence to figure out exactly where that problem occurs. And you can get the problems corrected much more quickly this way. You get more energy, more dollars, and your sites just run better. So that's all I had for today. Hope you enjoyed the webinar, and look forward to seeing you again.